step back and look at induction just one more time. The formula that it is so induction again. The formula of the geometric progression, calculus 2. Remember? Well, what is a geometric progression? What makes it geometric? Yeah, you multiply, right? You multiply every time by a value. So n plus 1, it is a recursive formula, n times r. Okay, so that's the growth. Multiplicative, it's like what is it? It's like a bank account growth. You multiply by, say, 1.1 to get the growth of 10% annually. Or it is you multiply by 2 if a certain population doubles every year, or every day maybe bacteria double in numbers. Okay, something like that. And then so it's easy to figure out what the formula is. So that's recursive. An is equal to a naught Rn. Okay, so that's the explicit formula, but that's not it. Even though, well, actually, technically, well, it just occurred to me that every recursive formula actually, when you transition to an explicit formula, which is what just happened. So this is recursive, and this is either explicit or functional, direct. I'm not sure which word is the best. Direct. So you see the difference, right, between these two formulas. So either you compute the next one based on the previous one, that's the recursive formula, or you have an explicit. Your formula depends on n. That's the depends. It depends on the previous element in the sequence, or it depends on n. Okay, so this is, like I said, calculus 1. Transition is very easy, but if you think about it, this is induction. So this, how do we transition from the recursive formula to direct formula? By induction. So that's you can say this is a theorem. Proof by induction. It is a very simple example of a proof by induction. Why? Because the transition has been specified to begin with. Okay, so implies. Okay, so by induction, base P1, let's say P1. Okay, P1 is A1 is equal to A naught times R first power. Works out, right? So just compare the, well, let me put it this way. Where is the base? If I put n equal 1, if n is equal to 1, n equals 0, then I have A0 plus 1. Let me start over. I think it is worth doing it in slightly more detail. So base, base, let n equal to 0, then A0 plus 1 equal A0 times R implies, I'm rewriting the whole theorem, A0 A1 times R1. Okay, so it's equivalent actually. A1 is equal to A naught times R1. Okay. A1 is equal to A naught times R first power. Okay, so that's I took the base of induction. I took the assumption on the left, plug in n equal to 0, so that's how I got the equation, and then I just rewrote it slightly. This is what I'm talking about. I rewrote slightly, so A1 is equal to A naught 2 times R in the first power, which is, so this is then P1. Right? We'll compare. So this is Pn right here, what we're trying to prove, and this is P1, right? Pn is there, and we have demonstrated that P1 is true based on the on our assumption on the left. Okay, so now I don't have to. I should. So Pn is just, let's write it out just in case. N is equal to, so that's my statement, my proposition that I'm going to be proving. I'm sorry, I'm going to be assuming. This is assumed, and then I go with Pn plus 1, An plus 1. So substitution, literally, I replace N with N plus 1, A naught R N plus 1. Okay, so that's Pn plus 1, and to be proven. Okay, so any thoughts? How do I get from Pn to Pn plus 1? Well, so the plan is the same, so you could try to so take the Pn plus 1 and sort of turn it around a little bit to see if you can do anything with it, or to find Pn and Pn plus 1, or vice versa. You start with Pn and convert it to Pn plus 1. Yeah.
Can we try Pn plus 1 minus Pn? So we take An plus 1 minus An.
Okay, so the idea is consider the difference.
So then An plus 1 minus An would be A1. So we just try to get A naught times.
Are you sure you stick with the word difference? An plus 1 minus An, is it that what you're talking about?
Yes. And then that should be A1, right?
No.
No?
No, you're thinking right, is just the word is not the difference. The operation is not the difference, but yes, you divide.
Yes. Okay. Yes. Okay.
Okay, then there we go. So then we have then, which is the answers are. Okay, or it should be. If this is true, then this is true, and then but where does it come from? It comes from Pn. Okay, so there you go. That would be the idea of the proof. Indeed, finding Pn in Pn plus 1 or Pn plus 1 in Pn, either way. What is the, so that is what we just written, is more like an idea of what we could, how we discover how we carry out that step. If you want to write it out carefully, then what do? I go with An plus 1. So I'm looking at Pn plus 1, I'm trying to get from left to right. Okay, so An plus 1 is, and now I'm using the recursive formula, which is at the very top. It is An times R, right? So by assumption. An plus 1 is equal to An times R. That's the definition of the geometric progression. And then by assumption of the theorem, because there is another one. There is the assumption of the inductive assumption. So the first step I make is by assumption of the theorems, which is this. Okay, so that's what I'm doing. Assumption of the theorem. An plus 1 is equal to An times R, and then I'm using the assumption of the this one, using the assumption of the induction. Okay, so which is, I substitute An into An plus 1. An just substitute here. So equal A naught Rn times R by inductive assumption. So inductive assumption, this will plug in. So A naught times Rn, and then we are pretty much done, because it's A naught times Rn plus 1, and that's all.
Why do we need to consider the division?
No, well, it was your idea. For the most part. I mean, it works out simple. It doesn't mean that you discover it instantly. So you tweak and you look at different angles and you look at difference, quotient, and then you'll find how to do it. That's like analysis part over here, analysis, and then you write up the theorem, and then how you discovered the solution becomes less important. So that is especially straightforward. As you can see now, that the whole proof is the meat of the proof is the last two lines, and it is very short. So it's certainly shorter than what we considered. But that's not the what I was actually aiming at. Even though, once again, any recursive formula will require the conversion from a recursive formula to a direct formula will require induction. So as another example, it is about, so that was about geometric progression, arithmetic progression. Since we're talking about this, so an plus 1 is equal to an plus b. Okay, so that's the difference between geometric, which is based on multiplication, multiply, compounded interest like that, or you deposit a fixed amount of money on your account every time. Okay, so that's recursive once again, and there is an explicit formula. An is equal to, what's the direct formula? You need a naught, obviously. So say a naught is equal to 0. How about that? A naught plus b not to the n times n. I should have put here a naught. No, there is an a naught. Okay, so there's not a problem. Okay, so then you are in the same exact place. So that's your homework. Prove by induction. Any recursive formula you can think of. Well, everybody knows Fibonacci sequence, maybe.
Heard of it. I've seen it before, but I forget.
Right. So it is defined recursively. So you add the two lost elements rather than one, and then deriving. And then there is a formula. There is an explicit formula with all those square roots. And once again, you have to go through induction in order to prove it. So this is, I think, this fine example. Then let me give you another example, and that is the progression. Rather than that's more calculus 3. It is about geometric progression. That is about the sum of the geometric progression. A naught Rn from 0 to n. M. So remember that transition. You study sequences in calculus 2, and then you start doing series. And before you get to series, and then one of the series that actually is manageable is the geometric series, which is simply made of the geometric progression. Okay, and this is a very important sequence because it takes you to Taylor series, as a matter of fact, because it's about powers. So it is in fact about Taylor series, Taylor polynomials, approximations of functions. So that's certainly a very important series. But before you realize that, it can be actually you got to figure out when it is converges, when it diverges. So then what you do is you got to figure out the formula. The formula of what? What does this is called? If I take my sequence or series and add it up to m elements, it's called what? It's called a partial sum. Partial sum, and then you take the limit of that partial sum, and that will be your whole series. So we're not going to be doing limits, but you need a formula for this in order to, an explicit formula, a formula that depends on m. in order to take its limit. Because if you try to take this limit with m going to infinity, you see what's happening. You'll have more and more elements, and then it's pretty much impossible to figure out what it is. So you have to do this algebra, hard algebra work before you get to actually do calculus. So then there you need a formula, and the formula is what the hell is the formula? Well, let me take a naught out. It doesn't matter anyway. Rn minus 1, R minus 1, I think that's what it is. M over here. Okay, well, so when you're not sure about the formula, well, you do base anyway. So if m is equal to 0, that's not working out. If m is equal to 1, okay, so we got to have m plus 1 over here. Okay, so once again, let's verify it. So if m is equal to 0, then there is only one term in the sum on the left. And does it work out? Yes, it does. M is equal to 0. The fraction on the right disappears, and you're left with a naught. Okay, so that's the base. And then you move on to the next step when r is equal to m is equal to 1. So m equal to 0, we have a naught equal to a naught. And you go with m equal to 1, then you have a naught plus a naught r on the left. And what do you have on the right? You have r squared minus 1 over r minus 1 a naught. Is it true? So we already do have a base, but one base is sufficient. But still, if we look at the second formula, do you see if it is correct? Well, long story short, yes. This is equal to r plus 1 a naught. You need to remember the difference of two squares. So difference of two squares will be r minus 1, r plus 1. You subtract, and then you divide, and then you're done. Okay, so as long as r is not equal to 1, this kind of geometric series converges, or it doesn't necessarily converge. We have a formula when r is not equal to 1, and then depending on the value of r, you might have convergence or divergence. So you can guess what happens. So I'm not going to go into calculus, but what? Yeah. So you remember vaguely, I suppose. So this is only about the algebra. So as you can see, we're not going to do any limits, but proving that formula is crucial, and it is done by induction. So once again, prove by induction. Whenever you have summation, it is also a recursive formula. Remember, that's what a series is. You keep adding elements. You know what the next element is. It's the previous one plus the term from the sequence. Okay, so in other words, that suggestion was that we discarded about looking at the difference. It will be about the difference this time, because you will be subtracting the m plus first element minus the mth element, and that is that's what you need to sort it out. The algebra is not really that much worse. Okay, so just a few examples of proof by induction from calculus and elsewhere.
So will there be calculus on the midterm?
Not literally, no.
Not what?
Not literally.
That's like not legally.
Not literally, because well, this one is kind of calculus. So you saw it in calculus, right? But on the other hand, calculus in the narrow sense is about limits, derivatives, integrals, something like that.
Keep it like algebraically.
Right. Algebra, yeah. So if anything comes from calculus, it might be either algebra or it might be geometry, something like that. Yeah. Okay, so let's move on. We will still could talk a bit more about it, about the test tomorrow. So let's review what we have accomplished. So we understood the inverses. We demonstrated that for or at least we demonstrated part of, that for the inverses to exist in the first place, the function has to be 1-to-1 onto, and conversely, if it is 1-to-1 onto, it has the inverse. The profound consequences, or of many, we pick one that interests us especially right now, is the composition of two bijections is a bijection. That's comes from this proof over here. 1-to-1 onto is 2 1-to-1 onto is 1-to-1 onto, and same for 2 1-to-1s compose into 1-to-1, and 2 onto functions compose into onto. So that is why two bijections give me a bijection. Okay, so that is not the end of the story. So let me point out a related issue for you to think about. So every little theorem has always other questions, related questions. So the question is, what if one of these functions is not onto? Okay, so when both of them are onto, the result is onto. What if one of them is not onto? So F composition G, one of them is 1-to-1. So that's H. Does H have to be 1-to-1? And same with onto. So it's 1 and 2. 1 onto. Okay, so does H have to be onto as well? Okay, so once again, think about it as a homework. Yeah, so it's related, and as you can see, you're sort of expanding the reach of the theorem. So we prove the theorem, right? But as the mathematicians, we explore a theorem and try to see, is it as strong as it can be? Can we weaken any of the conditions in order to, and still the conclusion would still hold? So two 1-to-1 functions give us 1-to-1. What if one of them is not 1-to-1? Is it still 1-to-1? Okay, so then when a question is posed this way, you have to then investigate, and the investigation is examples to begin with, and one single example can kill your conjecture, which is useful. So if, for example, you point out the example of F is 1-to-1, G is not 1-to-1, and the result not 1-to-1, okay, then the problem is solved to that extent. But actually it matters which one might be 1-to-1, first F or G. Okay, so I'll just leave it for you, or maybe you have a thought. Two functions that are not, one function is onto, but the other one is not. Does the composition have to be onto? X, Y, Z, F first, and then G. Suppose G is onto. So, like this. So it covers the whole thing. I'm trying to visualize it. So suppose G covers the whole Z. Okay? But F does not have to. So suppose this is my F then. So as you can see, I'm trying to suggest that it does not cover the whole Y. Okay? So what's the conclusion from this picture? What about H is not onto, right? Right. You can see that there is no counterpart here. So some of the Z's will be missing. Okay. So at least a suggestion. Then you still have to write it out. But that's where ideas come from little diagrams, visualizations, and examples. Remember what I told you yesterday, that most of these ideas can be illustrated with nothing but like two elements per set. So, and that can be illustrated with 2 elements per set. And you don't have to, if you are looking for a counterexample, there is no requirement that counterexample has had to have some kind of level of complexity. It could be as elementary as you pick. So you don't have to go to calculus for examples. Pick two elements and see two sets with two elements in them, or one, and see if it works out. You can illustrate this with each of them has two elements. Or how about x has one element and y has two, and z also has two. Okay, you see what I'm saying? So f is not onto, can't be onto because there's only one element there, and there are two in y. G is one-to-one onto, as a matter of fact, but you can see the composition cannot possibly be onto because, because it's because the codomain has two elements. You can try to similar analysis to this to the other problem, apply to the other problem. Okay, so that is big advancement, and we're gonna question. Yeah.
Will this be a good proof to do like by proof by contradiction, where you just find one example of a function?
A counterexample is not technically proved by contradiction. It is, well, I mean, it's not, because there is no proof. You just show that this particular example, as specific as possible, you show that it satisfies the hypothesis of the theorem, but not the conclusion of your hypothetical theorem. And A implies B. You show that it satisfies A, but not B, which means that, well, the theorem is not true, the end. So there's really no proof technically. You're not proving A implies B, B implies A, or anything like that. You just one example as specific as you like, as simple as you like. So that works totally. That's a counterexample. You just want to. All you have to do, if you don't, you shouldn't feel satisfied with a picture like that. It is only the idea. So what do? You actually write out this is A, this is A and B, B and C. The elements in these sets, B and C, and D and E, are elements, and write out what you write. F of A is equal to C, G of B is equal to D, G of C is equal to E. And that pretty much, with this you can write out the proof, not the proof, but rather demonstrate that the conclusion is incorrect very easily.
And how would you translate a counterexample into a proof then, or is that possible?
Well, you can say, well, suppose that it is well, the contradiction, right? So the theorem says that for every set, for example, this is satisfied. Okay, then let's assume that this is true for every set. And then what do? You show, well, there's a set for which it is not satisfied, a contradiction. So technically it is a proof by contradiction. It's just usually not called this way. Primarily, if you never see it in the form of proof, you just, theorem proof. You usually just say it's a counterexample.
Okay.
Yeah.
So in this example, if you say, since H equals F and G, one of them is 1-to-1, does H have to be? You would say no, because there's an example.
It doesn't have to be, right? But it only answers half of the question. First question, half of it, because I pointed out, I chose G to be 1-to-1. What does it make a difference if F is 1-to-1?
So you have to show both cases.
You have, right, yeah, so it's actually four questions in one here. I only looked at 1 out of 4. Okay, so we'll get back quickly to that, to this shortly. But there is one more topic that I started here, over here. It is right at the bottom. The question is, where does the graph lie of a function between sets? The idea is suggested by these 3 examples from calculus. So I colored the domain with green, codomain with purple, and then you can see how together they form, not as a union, right? The domain and codomain, they form that place where the graph lives, but this is not the union, right? Look at it. Two axes form the plane. Yes, they form the plane, but they don't there is a lot of room left, which is neither there nor here. And the same thing happens with the other two examples. A line and a plane form the three-dimensional space twice. So how? And the answer is called the Cartesian product, a Cartesian or just product of sets. Okay, so the idea is all here. It's about pairs. It's about pairs of elements. Okay, so since the graph has to contain all x's and all y's somehow, and they are combined somehow between them, and so that we follow that idea. It turns out that you don't need to have any kind of particular structure on those sets like this. You can form a Cartesian product of two sets, very simply. So that's the definition. So given two sets, x and y, the Cartesian product of x and y is x cross y, all pairs x, y. Okay, so that's the whole definition. So once again, if you look at to test our definition, we look back at these pictures, ignore the graphs, just concentrate on x and y. See, I identified x and y, and then x and y in the example 1, 2, and 3. X is our numbers, y is our numbers. You form pairs of numbers. What do they constitute together? You constitute a plane. Okay, if you the number 2 is slightly more complicated because one of these elements is a number, the other one is a point on the plane. But point on the plane is two numbers. So if you form a pair from a number and two numbers, you end up with three numbers, and that's how you have your three-dimensional space. Okay, so these are calculus examples, and as it is frequently the case, they are more complicated than they deserve. Than our definition deserves, because sets could be way simpler than these. Let me pick a simple one. X is equal to 1, 2. Y is 1, 2, 3. So any thoughts on what this is? What I'm gonna.
1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3.
How many?
6.
6, right? So you could let's use the definition. So let's write algebra, and then we explain it with a picture rather than vice versa. So x cross y, I'm using the definition, so it will be as it was just pointed out. I let x vary between 1 and 2, and I let y vary 1 through 3. Okay, so altogether you have 6 possibilities. So every possible x is paired up with every possible y. Okay, so well, I'm pairing it up. So I choose x to be 1, and then I pair it with 1. Then 1 is paired with 2. 1 is paired with 3. Okay, and then I do the same with 2. 2 paired with 1. 2 paired with 2, and 2 paired with 3. That's it. Okay, so that's my set. You can illustrate it just to confirm that it has something to do with the product. You can arrange them like this. You can actually see, you can place x on the x-axis, and you can place y on the y-axis. Okay, so if this is x, then the two elements that we have are 1 and 2, right? And I place them on the y-axis, 1, 2, and 3. So that is, so the red one is x capital, and the purple one is y capital. I don't really need to name x's in any particular way. I just choose to place my sets within the reals for the illustration purposes only, and then it turns out that my product, these 6 points in green are in fact form my product of the Cartesian product of these two sets. Okay, so a bunch of examples, obviously. That is probably one of the simplest examples. The one thing probably you can tell me the answer. X cross Y. How many elements? So that's what the vertical bar stands for.
Number of elements and X times the number of elements.
Right, right. Okay, so as long as these are finite, at least, and then with infinite we'll figure it out later. So as you can see, that's fairly transparent when the sets are finite. But if they're infinite, then you can pick examples from geometry plentiful. For example, if x and y are intervals, 1, 2 cross 1, 3. Two intervals. I take the cross product. What's the result? What?
You say how many possible things are?
7.
What?
7.
What?
There's 6, right?
No. I'm not. These are compare the compare. See the difference from the previous example. The previous example, x contains exactly 2 elements. Now x contains infinitely many elements. It is a whole interval. And y is the whole interval.
Okay.
Let me help you out. The picture is not really that different, but or it is placed in the same way, in the same place. 0, 1. X is the whole thing,
Okay.
and y is the whole thing. Now, not just this. It goes all the way from 1 to 3. So that's my y.
Why does that one go from 0 to 1? Should it just go from 1 to 2?
I'm sorry. Yeah, so it goes from 1 to 2. Yes, 1 to 2. Okay. So that's my x, and y is interval from 1 to 3.
So it's just that big block, you shade it all in instead of making dots like the top one?
There will be how many dots?
And
Infinitely many, right? For each x, there will be, right. So what's the result?
Just shade it in, right?
Well, you can describe. There is a word for that geometric object, rectangle, right?
Okay, well, that's what I meant right there. Yeah. Shade it in.
Okay, so for each x, it says think about it this way: for you pick x and you attach a copy of y to it above it, okay, and then you build them all up, and that's how we get a rectangle. Or you twist it, and for every value of y, you attach a copy of x, and you do it every time. And once again, another way to get that rectangle. Okay, think about, well, so what if I have 3? 1, 2, 1, 3, 1, 4. What is this? So this is a rectangle as we have just established. What if I have 3? What? It is a box, yes, a box. So you can see it is a very important operation. You can build so many things by taking Cartesian products. So intervals, closed or open, will give you rectangles, give you boxes, as well high dimensional spaces. So that's the thing about set theory. We're not limited to any dimension in particular or visible. And well, here's a trickier question. Backwards, represent the cylinder as the product. Cylinder represented as a product. No, product, Cartesian product. So in the same manner we just have. So it's not a calculus issue. Well,
Circle
times, yes. Times segment. Circle times the segment. So, like this. So this is my x, and this is my y. Okay, so once again, I'm thinking about this is a solid cylinder. So I take the whole disk. So for each point on the disk, I take a copy of Y and attach it. Attach. Okay, so that creates this kind of log, not not natural log, but just log, cylinder. Okay, if you want to have if I want a hollow cylinder, what do I do?
Take the circumference.
Right. Well, take this. Right. So replace disk with what we usually call the circle is the one that does not have the stuff inside. So that's another way. So you can just build so many different things. But our point was we're not going to explore this too far. The point was actually to introduce have a place for the graph. Where is the graph located of a function of two variables? And the answer is it is located inside the product, the Cartesian product of the two of the domain and codomain. Okay, so let me state that. Or it is a definition, as a matter of fact. So suppose f from x to y is a function. Then its graph is a subset of x cross y, Cartesian product, given by the formula that is familiar. There is no special word for it, notation for it, but I'll just write graph of f. So here's xy in x cross y, y equal f of x. So that's the definition of the graph that wherever or whenever it comes up in calculus, that's what you write, except it is usually x is a real number, y is a real numbers as well. So then the graph lies in these examples we started with in one numerical function from real to real. Then the graph lies in real cross real, which gives you a plane. Okay, if however we're talking about say parametric curves, then the domain is real, codomain is a plane. Together they form R3, and that's where the graph lies. Okay, so the graph of a parametric curve lies in the three-dimensional space. Similarly, but flipped, if a function of two variables is what you're looking at, then the domain is two-dimensional, codomain one-dimensional. The whole thing lies in the cross product, in the Cartesian product, which is the three-dimensional space. Okay, so that way you can have a graph associated with every function of any dimension, and that's you face it sooner or later, even in calculus, when you progress to high dimensional spaces. So, for example, if you have function of n variables, where does its graph lie? A function of n variables, where is its graph? What?
I'm not sure.
So z is equal to f of x1, x2, xn. So this is x, and this is, well, let's throw out z. Let's make it y. So combine x's and y's. Where does the graph lie? What? It will be in the Euclidean space. What dimension? N plus 1. Right. Okay, so this is marking the last topic for the test. Okay.
Wow.
All right. I'll see you tomorrow.